Hello, class. Today we are going to discuss some key ideas behind polyatomic ions, expanded octets, and then some exceptions to the octet rule that we have yet to see. And this will lead into a discussion of how to draw polyatomic ions. We're going to use some formal charge concepts and apply them to our polyatomic ions, and then look at how that makes these things bond in a more stable way. So polyatomic ions are stable covalent compounds with an overall charge. Can be positive or negative depending on the structure. And the charge actually helps to make them more stable. Typically, polyatomic ions end up with an odd number of electrons. And so gaining or losing electrons helps to stabilize them. When we look at Lewis structures, the majority of compounds with Lewis structures have even numbers of electrons. Odd number electron molecules do exist, but they're referred to as what's called a radical, and they are unstable and therefore very reactive. When we draw Lewis structures for polyatomic ions, we put brackets around them, and we place the charge on the outside. When we have a charge, we know that gaining electrons makes us negative in our charge, and losing electrons makes us positive in our charge. So what that does is it actually affects our total valence electrons when we go to draw a Lewis structure. So to figure out the total valence electrons for a polyatomic ion, we need to add the charge when we are negative, because that refers to the gaining of electrons, and we need to subtract the charge when we are positive, because that refers to the losing of electrons. I do have an example of each of these. For ammonium here, if we look at NH4+, you have 5 valence for your nitrogen. Each hydrogen has 1 valence times the 4 hydrogen present in the molecule. Overall, it gives us 9 valence electrons. That is an odd number and is not very stable for us. So we take account that charge. If we have a positive charge, we have lost an electron, so we subtract 1, and we end up with 8 total. Nitrogen ends up being in the center, and we form 4 bonds with it because each hydrogen can only have 1 bond. Now, one of the things we may have talked about previously with formal charge, if you watch the video on formal charge, is that the overall charge of a molecule is determined by adding up the formal charges of the individual atoms within the molecule. So if we go through and check, hydrogen we know normally has 1 valence. We subtract the number of dots around that particular atom. Hydrogen never has any dots around it, at least when we're doing these kinds of structures. And then we subtract the number of bonds. 1 minus 1 is 0, and each of my hydrogens have the same electron structure, so they all have formal charges of 0. When we look at nitrogen, nitrogen has 5 valence electrons. In this particular case, there are no dots from lone pairs around my central atom, but we do have 4 bonds. So 5 minus 4 gives us a positive 1. If we add the positive 1 and the 0 together, overall we get a +1 charge, which matches up with this charge on the outside of our brackets. Now, if you are unsure where that calculation came from, remember that formal charge is equal to the valence electrons minus the non-bonding electrons, aka the electrons that are part of a lone pair, and then minus the number of bonds that we have. So we could go ahead and check that for cyanide, CN1- on this side. Carbon normally has 4 valence, nitrogen has 5 valence, but this negative charge means we've gained an electron, so we actually have to add 1. So when we go to draw our structure, we end up with 10 total electrons. If I were to draw this from scratch, I have my skeleton here. I've used 2 of my 10. I go through and I can do my octet. Now I've used 8 out of my 10, and I only have 2 left for carbon. Obviously, this does not satisfy the octet rule, so we have to form some multiple bonds here. So I'm going to take a pair and make a bond. Still not enough, so I have to take another pair and make another bond. And that's where the triple bond comes from in my cyanide molecule. So then I can go through and do the formal charge for each one. Nitrogen we know has 5 valence, minus 2 dots from the lone pair, and minus 3 bonds from the triple bond. And we end up with a formal charge of 0 on the nitrogen. For carbon, we've got 4 valence electrons, minus 2 dots from the lone pair, minus 3 lines from the bond. We end up with a -1 charge on my carbon. If I add my formal charges together, my overall formal charge is still a -1, and that matches up with what's in the brackets over here. When we're talking about polyatomic ions, a lot of them have different purposes. Cyanide, in particular, is actually a poison, and it works the same way as carbon monoxide does. Sometimes people refer to carbon monoxide poisoning. That's why homes nowadays are fitted with both smoke detectors and carbon monoxide detectors, because they're referred to as a silent killer. Cyanide is very similar in structure to carbon monoxide, and it functions in the same way. So to look at that, we can look at some biological connections. We know that in our blood, we have an iron-containing complex called hemoglobin, and the iron-containing complex has a site available where it can bond an oxygen molecule, which is O2. That's the oxygen that we breathe. So when it binds that oxygen, it carries it through your blood and delivers oxygen to different parts of your body. And the way cyanide ends up working, and same with carbon monoxide, is it bonds that exact same site on the hemoglobin and prevents rather the oxygen from binding, and thus your cells are without oxygen. There are some exceptions to the octet rule that are worth discussing now. I mentioned it earlier that some molecules may end up with an odd number of valence electrons, making it impossible to have an octet. An example of this would be NO, the NO molecule. This is an example of something called a radical. We won't see a ton of those in our course here, but it is good to know that they exist. These things are unstable since there is an incomplete octet, and therefore they are very reactive. Some central atoms can have more than 8 electrons due to having electrons in the d orbital. So far, the central atoms we've looked at have s and p orbitals, which means in total you can have 2 electrons from the s and then up to 6 electrons from the p, which gives us our 8 for our central atoms here. These atoms are usually found in period 3 and higher. When we have a central atom like this, we can typically add either additional bonds in the form of double bonds or lone pairs to our central atom. And the goal of the expanded octets is to reduce the formal charge of the atom. When we're talking about formal charge, it's better to have as many neutral atoms as possible. So forming an ion and then reducing its formal charge by making additional bonds with the central atom is usually the way to go to do that. Now, this only works, again, if the element is in row 3 or below. So anything elements 1 through 10, it would not qualify for an expanded octet. So don't ever make additional bonds with nitrogen or oxygen or carbon. They max out at 8 valence electrons. If you're talking about things like sulfur and phosphorus, bromine, chlorine, iodine, those things are usually a good bet that they can have an expanded octet when they have when they're central atoms. So an example here of an expanded octet with phosphorus. Most people, when they go to draw phosphorus, they know that there are 32 valence electrons. Let me double check that. We got 5 from phosphorus. Each oxygen has 6, so 6 times 4 is 24, plus 3 from that charge, and yes, that does give us 32. Phosphorus ends up being in the center. Most people, when they go to draw this particular one, give it all single bonds. And when they do that, they give enough electrons, they use all 32 electrons, and they get a perfectly good structure that satisfies the octet rule, just like this. The problem is, when you calculate the formal charges, each of these oxygens end up having a -1 formal charge, and this phosphorus in the center ends up having a +1 charge. So as a result, you've got formal charges all over that molecule. And to reduce a formal charge, what we could easily do is, instead of leaving each of those oxygens as -1, because that's a large spread of electrons, we could take a pair and expand our octet to form an additional bond. By doing that, you've now reduced the formal charge of 2 of your atoms. This one is now 0, phosphorus is now 0, and then you end up with only 3 negatives, 3 -1 formal charges, and that adds up to your overall formal charge. This works because phosphorus is in that third row. It does have d orbital electrons that can hybridize with it and create an expanded central atom. This also typically occurs whenever we've got atoms bonded to the central atom that are more electronegative. So oxygen is more electronegative than phosphorus, so it's pulling electrons away from phosphorus, even though it appears that 10 electrons are being bonded to that central atom. In reality, when we're looking at the electron clouds around each of these atoms, they're kind of skewed towards each of the oxygens. Same idea occurs with phosphorus when we're looking in PCl5. Chlorine is really electronegative. It's more electronegative than phosphorus, and electrons are being pulled away from phosphorus, so they form an expanded octet as a means to gain enough electrons to be stable. In our next video, we'll go through a couple more practice problems dealing with polyatomic ions, and then we will also look at some resonance. That is all for now.